sound and the... Okay.
President of this jury.
Okay.
The jury is composed of Emmanuel Rio, who's professor at Université Paris-Saclay, José Manuel Lopez Herrera Sanchez, who's professor at the University of Sevilla, Sébastien Tanguy, who's maître de conférence à l'Université Paul Sabatier à Toulouse, and Stéphane Popinet, who's a research director here in D'Alembert. So, Ahmed, you have 45 minutes to expose your work, after which we will ask you some questions.
Wait a minute, apparently there's a problem with the YouTube sound.
Can you...
Jose, can you hear the...
I can hear now.
Yeah, you can hear now through the Zoom, but can you hear on the YouTube? You said on the
yes,
YouTube.
Yes, I hear in the YouTube.
Okay, so it's all fine for you. Okay, good. Okay, we can start. Okay, thank you.
Okay, so Ahmed, you have 45 minutes.
Okay. Well, hello everyone. Thank you for being here in my PhD defense on Hall dynamics in films, supervised by Dr. Popinet. I will start by a quick introduction to the topic, and for instance, few examples are of where you would one would encounter such a problem. For instance, in the painting and coating film industry, it's understandable that you wouldn't want to have the integrity of the film to be jeopardized by the existence of holes. In a completely different field of biology, there are DNA sequencing devices with very high precision that are designed basically on the concept of holes closing. And also in the field of fluid mechanics and environmental studies, you have the problem of bubble bursting, where you have the nucleation of a hole on a bubble cap, which eventually leads to the production of film drops. And film drops, along with other kind of drop production mechanisms as a result of wave breaking at the surface of the ocean, are an important means of exchanges between the ocean and atmosphere, which in turn have an impact both on local weather predictions and also climate models for the long term. But the focus from the top figure would be on the film drops, which are a major part of these aerosol productions. And this itself contains a series of complex dynamics, as described on the bottom image here, which starts with the nucleation of a hole on the bubble cap. And this hole on the curved film, which we call the bubble cap, is going to be the focus of this presentation. So the main question, to put simply, is that what happens after a hole, regardless of the puncturing mechanism or the condition before the hole nucleation, what happens after it's nucleated? It might be intuitive to think that any hole nucleation on the film would result in its bursting and disintegration. But it is known from literature and also from personal experiences sometimes that if you create a very small hole and if it has the right conditions, the film could heal and the hole could close on itself. And that's going to be the focus here. So when thinking of this problem, two main parameters comes to the mind. First is the thickness of the film and the size of the hole. And this happens to be the parameter that mainly determines whether the film would heal or burst. So this means that there is a critical ratio for the thickness to the film, for the hole size to the film thickness. And here on the top, I have a table that summarizes the primary works that have been done on this topic. And they are differentiated through different aspects that we are going to focus on this work. For instance, the focus here is on free films as opposed to films on the substrate, which are more extensively covered in the literature due to their applications in the painting industry. And also the focus is on understanding the hole healing mechanism and finding this threshold either analytically or numerically. And also, most importantly, finding the variation of this healing threshold to in respect with the other parameters of the problem, which requires us to consider the dynamics of the problem. And what we see from the table is that none of these primary works cover all these aspects that we would like to cover. And that's the foundation for this work that I'm going to present to you. And the method that we are going to use here is the using numerical simulations to solve the incompressible multi-phase flow Navier-Stokes equation that accounts for the surface tension term. But the gravity term from the Navier-Stokes equation is dismissed due to the fact that the time scale for the gravity to have any effect on the hole dynamics is much longer than the time scale that the hole evolves. And to implement these equations, we use Basilisk, which is based on C, to perform, based on C language, and to perform direct numerical simulations. And the immense advantage of using Basilisk is the adaptive mesh that makes it much more efficient when dealing with multi-phase flows that have intricate interfaces. But to be able to implement these governing equations, we first need to non-dimensionalize them. And for that, we have to select a set of characteristic scales within the problem to non-dimensionalize the equations. And for that, we select the thickness of the film, delta, as the length scale. For the time scale, the inertia capillary time scale, and for the velocity, the Taylor-Click or inertia capillary time scale. And for the pressure, the capillary pressure. And for that, with that selection, we end up with this set of equations, which is non-dimensionalized, but gives a rise to a non-dimensionalized parameter, which we're going to hear a lot in the following slides, and that's Laplace number, which compares the effects of surface tension in the problem with the effects of viscosity. So now we have the governing equations, non-dimensionalized. We need to select the governing parameters that we want to vary between different simulations, for instance, to see the effects of each parameter on the healing threshold. The problem is that there are various different physical parameters, 8 in fact in this problem, but from the Buckingham theorem we know that not all of these parameters govern the problem or impact the problem independently. So there is a dependency between those. We have to find those set of parameters that govern the problem independently, and using the Buckingham theorem we end up with 5 parameters. Here the Laplace number of the liquid, the Laplace number of the gas, the density ratio between the two phases, the size of the bubble, and the size of the hole, which if we think of it as the critical threshold for the healing and bursting, then this critical threshold should be a function of the other 4 parameters in the problem. But among these parameters, the viscosity ratio is not included, just to mention, and it's accounted for through the other parameters that we have here. And lastly, it's worth mentioning that during these simulations that we've done in this work, as a default set, we've used these values that correspond to a typical bubble bursting case in the oceanic context. And so we use these values as a default unless we want to vary any of them to see the effect on the healing threshold. And the last part to set up the method and to study the problem is to define the configuration and the geometry of the problem. And we are going to focus on 2 different types, holes on a flat film and holes in a bubble cap or a film with a curvature. So on the top that corresponds to the flat film, we have the geometry of the hole. The flat part is basically modeled by rectangle marked B here, but for the profile of the hole, it's an arbitrary choice of what to choose as the profile. And here we've selected a circle profile, which results in 3D to a torus that is connected at its half to the rest of the film. And when we apply the axisymmetric condition, it results in this model that is being simulated using the equations that we described. And in a similar fashion, we have the axisymmetric hole with the same shape on an axisymmetric half spherical bubble. Now, for the results, which are divided into 6 different sections, we start with just describing a little bit the healing mechanism and how it actually happens. So, at any point on the interface of 2 different fluids, you have these equations of balancing the forces you can write and end up with what is called the Young-Laplace equation, which basically gives you the capillary pressure as a result of the capillary phenomena, which basically, to put simply, is that any fluid would like to minimize its energy and thus its surface area. So if there is a curvature, it tries to cancel it out by creating this capillary pressure, which is connected to how much curvature exists. And this curvature H is the average of the 2 principal curvature at any point on the interface. And on the top figure, it describes how these 2 different curvatures could be calculated at any given point. And the fact that also we have to make an arbitrary choice, and here it's in this way that the delta P is calculated as the pressure inside the film minus the outside. And with that definition, we end up with the fact that the curvature, the center of which is inside the fluid, would be considered positive, and the curvature that is the center of which is outside would be considered negative. And that would correspond, for instance, here in this problem, to the hole size here. So since the center of curvature is outside, that would be the negative term, and the opposite for the thickness of the film. So in the first approximation, if you think of the healing, the whole healing problem, we could think that, okay, if the ratio of the hole size to its thickness is less than 1, then we have a negative pressure at the hole tip. And so there is a rush of fluid to that point, and that would result in the healing of the hole. And the opposite way, the opposite case would be the fact that the hole size is much larger than the thickness, and that would result in a flow away from the radial axis here that would cause the bursting of the film. Now that we've described the healing mechanism, it's time to see a way to find this healing threshold, either analytically or numerically. I start with an analytical hypothesis here. The key idea for which is to think about the forces that are exerted to the interface as a result of the initial capillary pressure due to the curvature of the film. And the fact that we know the average curvature for this particular shape that is as a result of this circular profile, it enables us to calculate the overall radial component of the forces exerted to the interface. So if we think of the healing or bursting problem as a race between some elements rushing towards the radial axis and some elements away from it, depending on their location, which imposes how much force in which direction is applied to them. If we think of the problem as a race between these two, then you could imagine that equating the sum of these forces to 0 would give some idea on the healing threshold, which here is calculated as dc equal to 0.57. And if we try to improve this, this initial step in the hypothesis, we can also account for the initial radial position of each of these elements on the interface, because it's the fact that whether or not any of these elements would reach the radial axis and cause the healing doesn't only depend on how much radial axis is exerted on them, but also how far away they are from the radial axis when the simulation starts from the initial position. So now we have a sum of radial distances covered by each element in one time unit as an estimate. And that would give us dc equal to 0.73, which when we compare to the numerical simulations that we did with this set of parameters, that corresponds to a case with minimized viscosity, compares well with the numerical simulation, 0.77. And the reason to choose a high Laplace number, which means minimized viscosity, is to make the comparison close with the hypothesis, because the hypothesis does not account for any kind of dynamical effects such as viscosity. So this was the hypothesis that we developed in this work, but there are also other works, such as the recent work by Stamp et al., that proposes a different shape for the hole and the film in a way that it would account for the mass conservation after the hole nucleation in a flat film. And with that configuration and using a comparison between the energy state of the two cases, they find this threshold that is much larger. And when we compared that to our numerical simulations for the same for the same configuration, we found a mismatch between what was predicted in the hypothesis and what we found. And lastly, primary work by Taylor proposed that the problem of holes in films is the same as the problem of soap film between two metal rings. And they study how to find a critical threshold for the existence of this soap film, which we know it takes a catonoid shape that has a zero mean curvature. And by finding a critical ratio for the existence of this soap film, they proposed that it would be the same as the healing threshold for the holes in liquid films. And when we compare their predicted ratio with what we found numerically, it's relatively close to the numerical results. And here I have the summary of what I just discussed about these three different ways to predict the healing threshold analytically. And we see that, for instance, the one important thing is that how the shape of the hole is connected to the rest of the film, because the rest of the film is just a flat part, and how it connects to the profile for the hole can either create a discontinuity in the second derivative of the geometry, which basically is the curvature of the interface, or a discontinuity in the first derivative, just a sharp angle here, or both, which is the case for the Stamp et al. Work. And what we see here as a result of discontinuity in the geometry is creation of a strong vortice that creates a strong flow initially, and that could disturb the result. And when it's two discontinuity on both of these factors, then the condition is worse. And so we see here that compared to these other predictions, the correlation between the predicted result and numerical simulation is very close here in what we presented, and also it's relatively good in Taylor's work, and on the last is the work with Stumpf et al., which has 2 discontinuity. So before moving to the main part of the results, which is about how the healing threshold varies between different parameters, I'm going to take a last look at the healing dynamics, and I'm going to zoom on what happens exactly near the healing threshold. So near the healing threshold, if you found it numerically for a specific set of parameters, what happens if you slightly change the size of the hole, and this drastic difference that one of them would end up in bursting and one of them would end up in healing, how does it work? What is the mechanism behind that? So 2 cases that describe such a situation are shown here, which start from the initial condition on the top, and they evolve to the last record of simulation here. And they have basically the same hole size, but with a marginalized difference. And what we see here is that they more or less follow the same trend. There's not a recognizable difference until at this point they start to deviate from each other, and one of them would end up retracting and bursting, and the other contracting and healing. And what we see is a recognition of a critical radial distance that is shown here, and we recognize by investigating more the parameters that we can measure from the problem, the fact that the mechanism behind this radical difference is the fact that there exists a critical radial distance upon reaching which the tip of the hole falls into a positive feedback loop that it cannot retract back from it. So here I have the figure that shows the evolution of total curvature at the tip of the hole for the 2 cases. And we see that the simulations start here, both of them follow more or less the same path, and this one retracts back at this point, and this one continues to reduce the radius and end up in healing. But the critical radius doesn't show itself here, but it shows itself in this figure, which is the components of this total curvature. So the total curvature, as we discussed before, is the sum of the 2 principal curvature, and at the tip of the hole, one of them is always positive, which corresponds to the thickness of the film, and the other one is always negative, which corresponds to the size of the hole. And we see here that the 2 cases start following the same pattern here. These 2 lines, red and blue, dashed blue, correspond to the positive component, and the black line corresponds to the negative component, which is the same for both of them. And we know it analytically, so that's how we can measure the positive component numerically, since we have the total curvature. And we see that at this point, the slope of the black line remains always higher than the slope of the blue line. And this is the result for, this is the condition that defines the positive feedback loop that amplifies the state at which they are. And what we can understand here is that the fact that this red line doesn't reach the radial, the critical radial distance, is the fact that they started exactly with this difference initially, and that results in one case failing to reach this point. It would be analogous to the same problem as when you're pushing a ball to the top of a hill, and if you have 2 balls relatively, like basically at the same position but with a marginalized difference in their initial position, and then you push them up, one of them could reach the top of the hill or the critical radial distance and fall over, which corresponds to the healing case, and the other one just falls short of and falls back for the bursting. Now, having explained how the dynamics and how the mechanism works for the healing, And the attempts that we showed for finding the healing threshold analytically and compared it to the numerics for specific cases, it's time to see how this healing threshold varies with varying different parameters of the problem. And we start with the flat film here that has only that the healing threshold here is only a function of three other parameters: the Laplace number of the liquid, gas, and also the density ratio of the two phases. We start with the density ratio effect, and here we see from the numerical results that a higher density ratio in fact increases healing threshold. And also what's interesting here is that in the numerical simulation that we did, the ratio below 1 actually corresponds to the opposite problem, which, so for instance, the normal case would be the liquid film in the gas medium, and the opposite way would be the gas film in a liquid medium. And we can see how this would have an effect on the healing threshold. And we can also see a dependency on the dependency of how strong this effect is on the Laplace number of the gas. So if the Laplace number is very low, meaning that viscous effects are higher in the film, then this effect of changing the density ratio is also more pronounced. And now, focusing on the Laplace number of the gas, we see the effect that more viscous gases reduce the healing threshold. And again, this effect is coupled with the choice of density ratio, which corresponds to different curves in this plot. So we can see that for a higher density ratio, the effect is minimized, and the opposite case for lower density ratios. And on the right, we have the power laws that we can find when plotting the same results in the logarithmic scale. And we find more or less a coefficient for these power laws that remain around the same number of 0.35. But it would also vary between the different cases with different density ratios. And the last parameter on the list is the Laplace number of the liquid, which focuses on the comparison between the surface tension effects in the film versus the viscous effects. And the main results that we see here is that by increasing the Laplace number of the liquid, we have an increase in the healing threshold. So the opposite way around to say it is that the viscous effects, if they are higher, it reduces the healing threshold in the film. And we can also see the power law and the coefficient that we find here. And lastly, the fact that this range that corresponds to these changes that occur between the Laplace number and the healing threshold also falls in the same range that corresponds to the typical oceanic bubbles and bubble bursting. So it makes it more important to consider the viscous effects if the problem exists in the context of oceanic bubble bursting. And for this last parameter and the last effect that we showed on Laplace number, I'm going to take a brief time just to explain the physical rationale behind the effect that we saw, which is similar to what we explored in the critical dynamics part. So here I have the same similar plot. One of them shows the variation of the total curvature at the tip of the hole as a parameter of the radial distance or the size of the hole. And the other one is the kinetic energy. So here we see that the same critical radial distance exists where the slope of these two curves flip and fall into the positive feedback loop. And here the mechanism behind the difference that we see between these two cases that have different Laplace number. So the red line corresponds to the one with lower Laplace number, more viscous, and the blue dashed line corresponding to a higher Laplace number and less viscous effects. One of them reaching this point and the other one not. So the mechanism here is the fact that the red line corresponding to higher viscous effects falls short of reaching this point because of having more viscous dissipation. Therefore, it doesn't have the required energy to exactly reach this point. And we can verify that in the plot for the kinetic energy of the two systems, where the red line has a lower energy before reaching this point. Therefore, it doesn't, and it starts retracting. In the process of retraction, of course, the velocity is increased and the kinetic energy is different from the other case. And we've described different effects that we saw from these changing these parameters, but we didn't talk about, okay, how did we choose the shape of the hole and what would be the effect? Well, of course, we don't know the exact shape for every nucleation. It would depend on the puncturing mechanism and various different conditions, but we can verify whether or not the effects that we just described with varying Laplace number or density ratio would remain the same if we choose different shapes. And that's what we did here. We considered 4 different shapes, and we did the same study for the Laplace number, exactly the previous slide. And we find exactly the same power law, not only the same effect, but the same power law with the same coefficient, which confirms the independence of arbitrary choice that we made initially to use the circle profile for the hole. Now we are going to change the focus on holes in bubble caps instead of flat films. So the main difference here in this case is that you don't only have a hole on a liquid film, you also have a gas flowing out of this hole due to the capillary pressure that exists initially, which directly is linked with the size of the bubble. The smaller the size of the bubble, the more intense the capillary pressure difference, and the more intense the gas outflow. And what we want to see here is, well, first of all, we can explore a bit the dynamics of this gas outflow. Well, if there is something going out, then the size of the bubble should shrink, and we first verify that. So QT here corresponds to the volumetric gas outflow. We can measure the average velocity going out, and we have the cross-section by the size of the hole that we measure. And we can compare this to the change of size in the shape of the bubble by assuming that it would remain spherical. And so we can find the rate of changes in the volume of the bubble, and we can compare them here, which they more or less compare well with each other. And this gives an estimate on the dynamics of bubble shrinkage. But more importantly, we can try to see if we can predict the gas outflow velocity, the average velocity going out, by simply thinking that this pressure difference is balanced by viscous stresses. So the balance between the pressure difference and viscous stresses should give you a velocity scale. And that's what we do here. So if you write this expression with this hypothesis, we end up with this relation that links the average velocity going out with the other parameters of the problem. For instance, the size of the bubble and the density ratio. And what this figure here verifies is this relation between the velocity and the density of the phases, or in other words, the inertial response of the gas inside the bubble. So the black line here corresponds to the default simulation using the default set of parameters, and we use those values to predict the mean velocity going out for cases where the density ratio is doubled or is halved. And because we have the relation here, and the symbols corresponds to the numerics, and the solid line corresponds to that relation, which shows a close comparison here. And lastly, in this section, when exploring the dynamics of holes in a bubble cap and seeing how the gas flow goes out, I also came across seeing this shape or this configuration when exploring the pressure field and the velocity field of the gas going out at the hole opening. So what I see here is very similar to what you see in the pipes for the Venturi effect, which corresponds or describes the effect that is observed when the flow experiences a change in the cross-section. which results in the increase in velocity and therefore a local drop in the pressure. And to verify whether or not this effect exists in the gas outflow, we can have the relation for the downstream velocity corresponding to the inviscid venturi relation that uses the pressure difference and the upstream velocity to predict the downstream velocity. And we can compare that to the measurement that we get from the numerical simulation. And we see that when the flow develops and the initial response is more or less completed, after the flow reaches the quasi-steady state at 2, more or less precisely it follows this relation here. And the relation is also compensated with a coefficient C that is there to account for viscous effects. So because in the problem, in the typical problem for the venturi effect in pipes, this C coefficient is there to account for the viscous effects, which is linked to the Reynolds number. And we also calculated the Reynolds number of the gas with this relation, and we see the same effect that is predicted for flows in pipes. Higher Reynolds number, less viscous effects, and a higher coefficient that is closer to the inviscid venturi. So overall, these results here show that yes, there is a venturi effect. But what we want to know more is that whether or not this gas outflow, the venturi effect, have an effect on the healing threshold. So for instance, to put simply, can a smaller bubble that results in a higher and stronger gas outflow result in healing larger holes? And now the last part, which is going to explore the question that I just mentioned, is to see, well, first of all, this question and also the variation between the other parameters. So the size of the bubble would correspond to the strength of the gas outflow and can have an effect by the venturi principle. And the other parameters, the density ratio and Laplace number of the gas, also could be explored. Before diving into the numerical results that we got for the venturi effect on the healing threshold, here is presented a way to predict this effect analytically. So if you go back to the same basic concept that we started from for the healing mechanism, we had two different pressure terms that were in action in opposite ways, one of them corresponding to the thickness of the film and the other to the size of the hole. And these pressure terms, whether or not they're balanced or not, would determine the healing threshold. And if we add the pressure drop that is associated with the venturi effect to these terms, then we can have a prediction on the venturi effect that we call here the venturi correction. And the equation the expression that we end up with here is links the critical size of the hole with the size of the bubble with inverse square, and also directly to the Laplace number of the gas. And we are going to see whether or not this holds to verification using the numerical results. Here, firstly, and maybe most importantly, we are going to see the effect of changing the bubble size and see if it follows what was predicted. So, using what we described for the venturi effect, if the flow is stronger, if it's going out faster, we expect a higher healing threshold. It can actually help the healing, which might be counterintuitive as it was for me when studying it. And this is what we see from the numerical results, that the healing threshold is in fact increased by decreasing the bubble size. So it confirms the venturi effect. But at the same time, we see that this effect is highly linked with what is the Laplace number of the gas. So if the Laplace number of the gas here is very low, so if the flow is very viscous, we basically see no effect. And if it's very high and the viscous effects are minimized, the effect is much higher. And this could be understood by the fact that, okay, if the flow is very viscous, then it would take, then there is a lot of viscous dissipation, and the flow might not develop enough before the hole closes or opens. So the time scales change here with changing the Laplace number of the gas. And here we plot the same results for the effect of the bubble size in a logarithmic scale to see whether or not it holds to the validation with the Venturi correction that we presented previously. So we would expect to see an inverse square relation between the size of the bubble and the critical hole size. And that's what we see here. So for different cases, if we plot the power law, we end up with coefficients that are more or less close to 2. And that's relatively a good prediction for the variation between DC and dB. But the same, unfortunately, doesn't hold true for the effect with Laplace number of the gas, with the effect of that on the critical threshold, where we would expect a direct relation, a power law of just 1, with coefficient 1 here. And that's not what we see, and at maximum we have 0.2. But this could be understood with the fact that we made an implicit assumption when driving the Venturi correction, and that was that the flow is dominated by viscous dissipation. We used this assumption when we were driving the average outflow velocity of the gas, which we use in the pressure drop for the Venturi in our derivation of the Venturi correction. But we see the effect qualitatively, but not holding to the same power coefficient that we predicted. And if we expand this range for Laplace number of the gas, we see that actually the results reach a plateau here. And what it shows is that actually the Venturi effect could be very significant if the Laplace number of the gas is high enough, or to put another way, if the viscous dissipations are minimized, are highly minimized, then we can even more than double the critical threshold for the whole healing for a bubble size of 20 in comparison with a flat film. And to conclude my presentation here, I will summarize the results that we discussed very quickly. So about what was related to flat film, we started by investigating the mechanism for the whole healing, and then we tried to see if we can find a hypothesis to find the threshold analytically, and we tried to compare it to the numerical results, along with exploring other hypotheses existing in the literature. After that, we tried to see what is the critical dynamics near the healing threshold, and we found the radial distance that was recognized based on exploring the evolution of the tip curvature. And we recognized the fact that there is a positive feedback loop happening after this radial distance. And lastly, we explored the variation of this healing threshold with different parameters in the problem, like what is the effect of viscous effects on healing threshold, or the density ratio, and also verifying that these effects are not dependent on the choice of hole shape. And on the other hand, for the same problem, but on the bubble cap, a film with curvature and existence of a gas outflow, we first investigated the dynamics of this gas outflow and the bubble shrinkage, but most importantly, we recognized the existence of a Venturi effect and verified it through the numerical simulations. And then we explored how this Venturi effect could change the healing threshold. We saw that for smaller bubbles, the healing threshold is increased. And we tried to develop a hypothesis that could predict this effect on the healing threshold, and we compared the power laws between the prediction and the numerical results. And lastly, on the prospects that could follow this study, well, there is a great potential to verify these results through physical experiments. So, for instance, we laid down the exact variation that we would expect from the numerical simulations that we got for different parameters. For instance, you could set up a simulation for two bubbles with different type of gases that correspond to different Laplace numbers, and see if you see the same trend on the effect on the healing threshold. And in terms of the numerics, one could incorporate the drainage of the bubble cap. So when the bubble rises to the surface, of course it's not a perfect sphere. The cap drains and the shape depends on the gravity, the size of the bubble. So the film thickness initially here is not realistic, and it could be improved by incorporating the drainage model, which we already have, but it's not incorporated into the model for the whole healing dynamics. And also we can account for the surface tension gradients on the film that would result in the Marangoni effect as one of the mechanisms that could augment the puncture, and also accounting for molecular forces, for instance, Van der Waals forces, as a way of producing a realistic puncture, something that today doesn't exist. And with that, I thank you very much for your time, and if you have any questions, I will answer. Thank you.
Thank you, Ahmed. So it's time for the questions. Okay.